So since I'm the first official speaker and organizer as well, I'd like to welcome everyone to the program. I would also like to say a few general things about it. So as you may have realized, there is a great variety of topics, so to some it may even seem collective, but there is a unifying theme, which is gravity. And the first half of the program is more geometric in spirit, with exceptions explained by availability of speakers. The second half is more about amplitudes. So that's the general structure. The first 2 days are concentration days on what can be called a connection viewpoint of gravity. So there is a series of talks. Today is the first talk on 3D gravity, and the approach that I'm going to describe is a way to think about gravity in both 3D and 4D. Well, actually 2 points there. One way is one takes a connection on a manifold as the main variable instead of the metric. And another viewpoint, which today I will explain for the case of 3D gravity, you can actually encode information about connection as well as the metric in a certain 3 form in a higher dimensional space. So in the case of 3D, it will be 6-dimensional space. So it's either connections or certain 3 forms in higher dimensions. This is a viewpoint. And well, I also put here a note saying that in some, well, actually this viewpoint that I'm presenting is not unrelated to Penrose's twistor construction. There are various relations, even though this is different, but there are relations. And conceptually, what twistor description of gravity tries to do is similar, right? Twistor description of gravity tries to encode metric into some other structure. Okay, so I want to say from the beginning that the usefulness of this way of thinking about gravity is not clear yet. At the moment it's studied because it's possible and it's beautiful, as I hope to convince you. But just the very existence of this description of gravity leads to a puzzle about 4D gravity, which I want to describe to you tomorrow. And the puzzle is that if you think about gravity in terms of metrics, then GR is a unique theory. There is really no freedom. We completely understand why GR is there. It's the only second order, second derivative theory of metrics that exists, at least in 4 dimensions. But in the realm of connections, this statement is not true anymore. And actually, we will see tomorrow that there is a certain other theory of 4D gravity in terms of connections, which appears to be more beautiful and better geometrically motivated than GR. So there is a puzzle why real world is described by GR. The fact that this puzzle exists is another motivation for looking into this. Okay, but today we will be in 3D, so this is the plan for both days. My talk tomorrow morning is a description of 4D gravity in terms of connection. Joel will give a talk, and tomorrow afternoon I will describe 4D and its 7-dimensional lift. So in the beginning, some very simple facts about 3D gravity. You probably or must know all this. These are very simple facts. So for concreteness, my 3D gravity will be a hyperbolic case, so lambda less than 0 and Riemannian metrics. But everything I say can be generalized with appropriate modifications to other cases. The only thing that is essential is non-zero lambda. So I'll describe metrics by the corresponding frame fields and frame fields. So in a 3-dimensional manifold, my frame field is one form Lie algebra valued. Actually, in my case, it will be anti-Hermitian 2x2 matrices. This is the way I think about Lie algebra. So one form, so with values in anti-Hermitian 2x2 matrices. The spin connection locally can be also thought of as a one form Lie algebra valued. Then there is a compatibility equation between the spin connection and the frame, or a zero torsion condition, which is that exterior covariant derivative of the frame with respect to connection is equal to 0. Here it's spelled out. And this is an algebraic condition on the connection, which can be solved like a fine spin connection in terms of derivatives of the frame, as usual. So there is a unique solution connection as a function of derivatives of the frame. Now, Einstein equations in this formalism are, Einstein equation is a constant curvature condition in 3D. Curvature of that spin connection, which is a Lie algebra value 2 form. The constant curvature condition just says that it's E wedge E. So this is our Einstein equation, and I use normalization lambda is equal to -1. Both compatibility condition between the frame and the connection and this Einstein equation follow as Euler-Lagrange equations from the simple action. This can be called Einstein-Cartan action. It's a first-order action for gravity, because field equations that follow are first-order derivatives. And if we substitute the solution connection as a derivative of the frame field back into the action, of course, we get the Einstein-Hilbert action with non-zero lambda. Okay, it's also useful for later to recall the Chern-Simons description of 3D gravity. This arises because one can note that both equations arise as real and imaginary parts of a single first-order equation, which is that the curvature of this combination of spin connection and the frame is 0. This is the statement of Chern-Simons description at the level of field equations. Another way to say the same thing is the relation between the actions. The Einstein-Cartan action is just the imaginary part of Chern-Simons action for this connection. This is the Chern-Simons action. There are also some subtleties about ambiguity of defining the Chern-Simons, but they, well, the subtlety is that the Chern-Simons action is not invariant under gauge transformations. And, well, for the purposes of what I'm saying, that's not, it doesn't matter. Okay. Now I will go to the pure connection description. It turns out to be possible in 3D and in other dimensions to use connection, spin connection, as a main variable instead of the metric. The way you do it is, remember, the way to go to the pure metric description is to solve for the connection in terms of the metric. But you can do the opposite. You can take the Einstein equation, this one, and instead, this is the equation that you obtain by varying the first-order Lagrangian with respect to the frame. So this is the equation for the frame. You can attempt to solve this equation for the frame. And here I will describe you how this is done. Of course, to be able to solve, so you start with some connection, you compute this curvature, and then you try to solve this equation for E. You want to find a frame which is defined by the connection, or metric which is defined by the connection. Of course, in order to be able to solve this equation, the spin connection cannot be arbitrary. There is some sign condition, which I will explain now. And the basic idea why you can solve this equation is that you can think about the curvature. Remember, this is a two-form with values in the Lie algebra. Two forms in 3 dimensions is a 3-dimensional space, and Lie algebra is a 3-dimensional space. So this is, you can think about the curvature as a 3x3 matrix. And basically, the idea of this metric is to think about the curvature as the metric. Roughly, this is what is happening here. So, but I can describe it more explicitly. To first explain the condition that omega must satisfy in order to be able to solve this equation, I need to introduce a sign of the connection. So to describe that, let me first define a map. This will be mapped from 1 forms to the Lie algebra, and the map is defined if I choose a volume form. I choose an arbitrary volume form on my 3-manifold V, and then I define a map. So the way this is done, I take my 1 form, which I want to map into Lie algebra, I wedge it with the curvature. This is a 3 form with values in the Lie algebra, and I divide by my reference 3 form. So I get the Lie algebra element this way. So this is a map. Then a sign of the connection arises because I can apply this map to the curvature itself. So what I do, this is described here, there is some factor which is just for convenience. But the essence of this is that, so curvature is, of course, is a 2 form. So I can apply, and this map is It's acting on one form, but I can apply this map to every one form slot of the two forms. So I apply it twice. This is the meaning of this tensor here. And the result of application of this map is a Lie algebra element, another Lie algebra element there, and the curvature itself is a Lie algebra element. So I get 3 Lie algebra elements there, and I take a trace. This gives me a number. And important thing to note is that, of course, if this volume form that I chose here is a completely arbitrary. I can always, well, it's better to fix an orientation of my manifold and don't touch it, but after orientation is chosen, I'm free to rescale my volume form by an arbitrary non-vanishing function, positive everywhere, so that I don't change the orientation. And then, looking at this formula, I see that here the map is applied twice. So, well, yeah, actually, even if I change the sign of this V, the sign of lambda doesn't change because the map here is applied twice. So the sign of this lambda of F is invariantly defined. Even if I change orientation of my manifold, I don't change the sign. So there is a notion of sign of the connection. And then,
sorry,
yeah.
So lambda F is a scalar.
Lambda F is a scalar.
F
Yeah.
and on V. On the choice of volume form.
It depends on V, of course. Yeah, if I change the V, lambda of F will change. But if I multiply V, say, by everywhere negative function, the sign of lambda will not change.
I'm sure you'll hate to do it. Could you just write it down in local coordinates?
I can, yeah. So
Oh, it's cubic in it.
it's cubic. It's
So
cubic
you
enough.
can just
It's cubic
snap
enough.
out all these
So basically, it's, this trace is an epsilon. There will be, yeah. The important thing is that it's cubic enough, and all indices, all space-time indices of F are contracted, and you use the epsilon tensor that you have. Yeah. But thinking about it this way is better because I will do very analogous construction in 6 dimensions. So I think without coordinates, it's a bit more clear. Anyway, so now this motivates me to introduce a sign of the connection. And actually, well, the sign and as well as a notion of what is definite connection. So first of all, connection is called definite if that map from one forms to Lie algebra is non-degenerate. This is a definiteness. And connection is called positive or negative definite. It's just a sign of this lambda of F. And then, well, I can define this notion locally and then everywhere. Yes.
Can I just check that I've understood this in my language?
Right, yes.
Let's go back one
Yeah.
slide. So definite says, so here this map F, you can
Right.
think of it as being a map from lambda 2 to little SU2 joule, say.
Yeah.
So definite says that's an isomorphism between 2 rank 3 spaces.
By isomorphism, I just mean non-degenerate, so non-zero.
Yeah, it has no curve.
Yeah, no curve.
And then both of those vector spaces are naturally oriented.
Yeah. Mhm.
So the sign just says whether it's orientation preserving or reversing.
Yeah, I think this is the same sign. Because this lambda is just the determinant of this map, essentially. So it's the sign. Yeah.
Okay.
I see. You can just think that the determinants of
You can think that, yeah, this lambda
a
is
three
just the
dimensional
determinant
space
of that.
to three.
Exactly. Yeah.
use the V to normalize the volume form.
Yeah.
But I guess the point I'm making is you don't need to choose orientations on lambda 2 or SU2. They have kind of they're naturally oriented.
Yeah.
Right.
So it's a 3-dimensional trick. So
So there is a sign to the connection. This is an important point, and there is a notion of non-degeneracy of the connection. And it's useful to think about what it means for a connection that comes from a frame, right? Because we can take some metric, a frame field, compute the spin connection for it. So what does it mean? What are these notions? What are these notions? So the map that I described is just the Ricci curvature. You can think about Ricci curvature, say, well, if you have frames, yeah, well, Ricci curvature is a 3x3 matrix. So my map phi, if I identify the algebra appropriately with appropriate things, my map phi is just the Ricci curvature map. So definiteness just asks the Ricci curvature to not have any zero eigenvalues. And similarly, the sign of the connection is just the determinant of reaching. So we're asking, well, therefore, the definiteness is a very weak condition. For example, a connection which have, you see, definiteness is just non-degeneracy. For example, I can have two minuses, one plus, and I can be positive definite, according to my definition. Okay, and then why do I need all this? Because for a negative definite connection, I can solve this equation for the frame. I can solve the Einstein equation, or I can solve the equation defining the frame. I can find frame as a expressed algebraically or constructed algebraically in terms of the curvature. Similarly, for connection of opposite sign, for a positive definite connection, I would need to put a minus sign in front of this equation to be able to solve it. So this is why the sign is important.
Or maybe you could get a complex one.
Yeah. But here I want to stay real. So for a negative definite connection, I can solve this and find E as a function of f. There is a local formula. Well, actually, yeah, this is a local formula. This is my proof of this statement. So first of all, I can define a certain canonically defined volume form from a negative definite connection. I just take a square root of minus lambda of f, and I multiply by that reference volume form that I used for the definition of lambda. This guy is invariantly defined because if I scale v, then this doesn't scale. So this is canonically defined volume form. And then the solution of this equation is explicitly written here. You see it's quadratic enough. My frame is quadratic enough, but then I need to divide by the volume form, which involves the square root of something cubic. So it's a complicated algebraic expression, but this algebraic expression solves f is equal to E wedge E. After this is solved, and it's important to understand that my frame is, because curvature is first derivative of the connection, I've expressed the frame field as the first derivative of a more basic object, which is a connection. So here I'm viewing connection as a potential for the metric. Metric is the first derivative of the connection of the basic variable. And then, again, it's useful to understand what is that metric that I get. Imagine I start from a metric. I start from a metric, compute the spin connection, and from that spin connection I compute the resulting metric. Well, this is what it will be. It will be it's basically the original frame, but twisted by the Ricci curvature. So only when Ricci curvature is an identity matrix, I would obtain the metric I started from. In general, I would get a completely different metric. This is what this procedure does. And of course, this formula also makes it clear that you get a Riemannian metric degenerate where Ricci curvature is degenerate. So if your Ricci curvature was having zero eigenvalues somewhere, the new metric will have degeneracies at those points. It's also clear that even though Ricci curvature may have minus signs in it, because my metric, I'm squaring Ricci. When I'm squaring the frame, I'm squaring Ricci, and so these minus signs will disappear, and whatever Ricci is, I will get a Riemannian metric from this construction. Okay. What is the pure connection action? The pure connection action is you just take the solution for the frame in terms of the connection and you substitute it back to the Einstein-Kaplan action. What you get is just volume, multiple of the volume of the space computed using the metric defined by the connection. It's a function of connections. Remember, this is just algebraic, sufficiently complicated algebraic object in terms of the curvature of the connection. So this is non-linear in first derivatives of the connection. Of course, as an action in terms of metrics, it would not be an interesting action. It would be just depending algebraically on metrics. It would not lead to any interesting equations, Euler-Lagrange equations. But as action for connections, this is interesting because this is non-linear in derivatives. So you will get some interesting Euler-Lagrange equations on this action. And we will see now that its critical points, of course, are just constant curvature metrics. So this is described on the next slide. Let's look at how you vary its action. What are Euler-Lagrange equations? First point is that I can write my volume, well, as just a trace of E, where E is the solution of that equation. F is equal to E. And now I vary. I can see that I can write the variation as variation of E, wedge E. But now this is curvature by definition. So this is variation of the curvature, and therefore it's the covariant derivative of variation of the connection, wedge the frame, and therefore you see that Euler-Lagrange equations are just equations saying that the connection is compatible with the frame that it defines. This is a second order PD on the connection because the frame is first order in the connection. So this is second order PD. And then another way to phrase what this Euler-Lagrange equation is that it says that the connection that you started from is compatible. Well, the connection that you started from is the Levi-Civita connection of the metric that a connection defines. So in a way, this equation says that the circle closes. You start with connection, you compute the metric, you compute for it the Levi-Civita connection, and you get back the same thing. And when this equation is satisfied, the metrics that the connection defines are automatically constant curvature, because by construction, F is equal to E wedge E. And now that this equation says that your connection is a Levi-Civita connection, well, this is just an Einstein equation. So this is how it works. In these connection descriptions, you always get Einstein equation for free by construction, and compatibility equation between connection and the metric is your Euler-Lagrange equation. This is typical. This will also happen in 4 dimensions. Okay, so this is almost all of my 3D story. Before I go to 6 dimensions, I also want to comment on possibility of having a gradient flow. There is a new functional here. Right? There is a volume functional defined. It's a function in the space of connections, volume function. One can talk about this gradient flow. Why this may be interesting? Well, we have another example where gradient flow of a function of connections is very interesting. This is the gradient flow of Chern-Simons. Right? As you probably all know, you can write this gradient flow, and this is first order equation. Chern-Simons is first order in connection, so this is first order. And the left-hand side is also first order, and this equation can be understood as a dimensional reduction of 4D self-duality equation. This is a 3D right-hand side, and you add time, so this is dimensional reduction of first order 4-dimensional equation, and this plays an important role in Donaldson-Whitney theory. So this suggests that we'll look at the gradient flow of the volume. Important point here is that to talk about the gradient flow of Chern-Simons, I need to choose a metric, reference metric in 3D, because I need notion of a star there that is given to you by the metric. So, and this is why it comes as a dimensional reduction of 4D self-duality equation. 4D self-duality equation, of course, depends on the metric in 4-dimensional space. The flow that I will describe now, you don't need any metric for it, because the connection will itself define the metric that you use. So this is my gradient flow. We already know that this variation of the action with respect to the connection is just exterior covariant derivative of the frame defined by the connection, and then you take a star using the metric defined by the connection. And then it's very easy to see that, well, first of all, the right-hand side, of course, is second order in connection, because the frame is first order in the connection. So this is now a heat type equation flow. And then it's easy to give this flow in interpretation. I can always write my connection as I just write it as the Levi-Chiliter connection for my frame, which by definition satisfies this, plus a torsion. And then this right-hand side here is basically torsion. And so, and the dual of it, again, will be linear in torsion. So this flow can be called flow by torsion. You change the connection, how torsion tells you. This is just an interpretation. Okay, this flow may be interesting. This is why I have to mention it here. And then I talk
It's
about
obviously parabolic. I mean, you're really a heat type equation.
Yeah, I haven't studied, but probably it is. Yeah, after fixing gauge, probably it's the good Laplace type equation flow. Yeah.
Do you have a formula for the evolution of the metric under this?
It's also not hard to work out, and it looks like it's a Ricci flow plus this torsion correction. So it looks like the way to think about the flow is you flow the frame as well as the torsion kind of separately, and then the torsion back reacts, and it appears on the right hand side. So
When it appears in the flow of the metric,
yeah,
is it just the torsion or is it derivatives of the torsion?
I think it's just the torsion, but these details
So
we
it's
can work
a
out.
lower order.
Yeah,
I mean,
but I haven't studied this in details. Only know very simple things about this flow. So this is one of the things I wanted to discuss. Okay, and then in the remaining time, let me give 6-dimensional interpretation for all this. So now instead of describing my metrics by connections, I want to do something completely different. I want to encode all geometric information into a certain free form in a higher dimensional space, 6-dimensional space in this case. The 6-dimensional space is going to be the total space of the principal SU2 bundle over my manifold. And the relevant 3 form is going to be the Chern-Simons 3 form in that total space. And you'll see that all the constructions that I described to you in 3D, the most natural way to understand them is by thinking in terms of 6 dimensions. So this is what I want to describe. Some basic facts about 3 forms in 6 dimensions. So first of all, the dimension of the space of 3 forms in 6 dimensions is 20. There is a notion of genericity or stability of a form. This genericity is just a notion. So you have GL6 acting on your forms, and stability just means that your form is in an open orbit of GL3. There is another form of the same type nearby. And the relevant orbits in the real case, there are 2 relevant orbits. There is a sign. So the relevant orbits is either GL6 divided by SL3, SL3. And in this case, the canonical, for a form of this type, for a form lying or living in this orbit, you can always write this form in this canonical form. It's a wedge product of 3 one-forms plus another decomposable guy. And the way to think about these SL3s is that they rotate these 3 one-forms into each other. And the other SL3 does rotates the betas. This orbit, I will call it of positive type. And another possible orbit is this guy, where the 3 form arises as the real part of a complex 3 form, which is the wedge product, which is a decomposable 3 form, and these alphas are complex 1 forms. And in this case, the stabilizer is SL3C, which just rotates these 3 complex 1 forms into each other. You can sort of convince yourself that this has something to do with 3 forms by just counting the dimensions. Well, here is the count. The dimension of GL6 is 36, so minus 8 minus 8, we get 20. So you see that at least the dimension of this orbit is the same as the dimension of the space of 3 forms in 6 dimensions. So the 2 orbits in real case, this is important. for negative type case, 3 form defines an almost complex structure. This is how it happens. So again, we will do construction of the type that I already described to you with connections. I'll choose a volume form, arbitrary volume form, in a given orientation class. And then I define some endomorphism of the space of one forms. So this is done like this. I take my one form on which I want to act. I wedge it with, and what I'm describing is a scalar. So the result, of course, I want the result to be one form, and I can describe the result by sticking a vector field into the result, right? So this is one form, and this is a vector field inserted into that one form. So it's a function. And this function is, I take the original one form, this is a 2 form, because this is a 3 form with a vector field inserted, and 3 form wedged. So overall, this is a top form, I divide it by the volume, I get that function that I want. So this is my endomorphism. Of course, it depends on the choice of volume form. If I multiply volume form by a function, I change my endomorphism. Then it's an exercise to check that this endomorphism squares to multiple of identity. This can be verified. For example, you can write it explicitly in terms of epsilon symbols, and then it's a simple exercise to check that it squares to multiple of identity. And then another exercise is that for negative type 3 forms, the scalar that appears on the right-hand side here, the coefficient in front of the identity is negative. And actually looking at this scalar gives another definition of stability and of a type of a form. The form is called stable if this is non-zero, and it's negative type if this is negative. So just looking at this object, you know the orbit to which the form belongs. Then, to define almost complex structure, essentially I just take this endomorphism and I normalize it so that it squares down to minus identity. You see, for negative type, I need to take square root of minus lambda, and this minus explains why it squares to minus identity. So this is an almost complex structure on a manifold. If for forms of positive type, I would not put a minus there, then it would square to just the identity. It would not be almost complex structure, but it would still be a useful map. Still do things with this map, but it would not define. So only for forms of negative type, you get almost complex structures out of 3 forms.
Really, really dumb question. If you chose to do the vector contraction into the second omega there, would that?
No, that wouldn't change. It's just a sign.
It's not the sign.
And you cannot, of course, for example, in 6 dimensions, wedge omega is 0, because it sounds like a region. So this is why you need to do something like this. You need to first insert the vector field, then take a wedge product, and then wedge it with another one form. Okay, so we define almost complex structures this way. Then there is a Hitchin functional of 3 forms at 6 dimensions. So for these forms of negative type, it's clear that you get volume form naturally defined. This just follows from the fact that, as you can see, this is quadratic in my k. So and remember, if I scale k, well, if I scale the volume, I scale k. So this lambda scales as a square of the volume, and therefore square root of lambda scales as a volume or inverse volume. So this guy is invariantly defined volume form. You just can check it by scaling. And so use this volume as a top form to be integrated, and this is the functional. Remember, it depends non-linearly. This is a functional, non-linear function of a 3 form. There are no derivatives here. And then Hitchin showed that critical points of this functional, if you vary your 3 form in a given cohomology class, if you vary by an exact form, critical points are integrable, almost complex structures. So here is a sketch of how this can be shown. One first shows that the volume form can be written in a useful way. It's a wedge product of 2 3 forms, where the other 3 form is obtained from the original 3 form. You just act in every slot of it with the endomorphism, with the almost complex structure. So it can be called the complex conjugate form in appropriate sense. So this is way to write volume form. Then one checks that variation of the action can be written as omega hat wedge variation of omega, and you see 1 over 2 disappeared because of some scaling, and because we said that we want to vary omega by an exact form, this variation is can be written as dB, and then immediately get Euler-Lagrange equation saying that exterior derivative of omega hat is equal to 0. And then there is some geometric argument why this together with closedness of omega implies that the almost complex structure is integrable. One simple way to think about it is that one can combine omega and omega hat into a complex 3 form, and then these 2 equations together imply that this complex 3 form is closed. And this complex 3 form is your top holomorphic form. So this is how to think about that. Okay, so critical points are integrable, almost complex structures. And then I come to 6D interpretation of those 3D constructions. So as I said, I want to take principal SU2 bundle over my 3D manifold. I have a manifold, I have a connection on it. Principal SU2 bundle, which is a 6-dimensional space. So this is necessarily a trivial bundle. I can almost write it as SU2 cross M or S3 cross M. Of course, not in any canonical way. Then, and then I want to take some SU2 invariant stable 3 form in this total space. One important point of this geometric construction is that now, when I'm in this setup of the principal bundle, my 3 form, remember it's just in 6D, 3 form, the only geometric object it gives me is almost complex structure. It doesn't give me a metric, it gives me almost complex structure. But now that I have fibers and metric in the fiber, I can define a metric. This is done as follows. So first of all, not only I can define a metric, almost complex structure in this setup gives me a notion of connection as well. The connection arises because I can, I have the structure of my 6D space is like this. I have a notion of vertical vector fields. I can act on them with almost complex structure, and I can declare the result to be horizontal. So provided my almost complex structure is good enough in the sense that it maps vertical into something that is not vertical, this gives me a good definition. So I get a notion of connection. And then I have a notion of metric. This arises because now I take 2 horizontal, I have a notion of horizontal vector fields. Now I take 2 horizontal vector fields, I map them back into vertical vector fields, and then use the Kirill-Krasnov pairing on vertical vector fields to define the pairing of horizontal. This gives me a metric. So if I'm in the total space of the principal bundle, with Kirill-Krasnov metric in the fibers, I get connection and a metric out of almost complex structure. This is an important part of geometry here. Then another important fact is that if you start with closed SU2 invariant 3 form in the total space of the principal bundle, with assumption that that 3 form integrated over the fiber is non-zero, then any such 3 form, closed invariant 3 form, can be written as sum of Chern-Simons of some connection and a 3 form on the base. This is proven just by, well, you write decomposition of an invariant 3 form, and then you convince yourself that you can always choose things appropriately so that this is So again, any closed tree closure, of course, is essential here to be able to write it like this. So it's a sum of chain assignments plus 3 form on the base, and 3 form on the base, any 3 form on the base is closed. And I can either think about it as, well, it's a sum of exact-piece and non-exact-piece on the base.
What happens if I double omega? I don't change the connection, right? Because
If you double omega, yeah, I think I also here, yeah, I chose the value for this, the scale, yeah, of course, yeah, I chose the scale. Which is always possible because I can always, the functional that I'm going to describe is algebraic in my omega, and I can always take an overall scale in front of my functional. So I chose the scale for omega appropriately. This would not be possible, it would not be a possible description if my integral is equal to 0. Then this doesn't apply. So important point here is that closed invariant 3 form in the total space of the bundle, it knows something about the connection. I already told you one way it knows something about the connection. This is this way. You start with your 3 form, it defines your almost complex structure defines the connection. This is one way. Another way connection arises is this way. You write that closed invariant 3 form as a chain assignments of some connection. Of course, this connection is a Lie algebra valid 1 form in the total space of the bundle. This is the geometrically well-defined connection. And this is a 3 form in the total space of the bundle. Okay, now I have another simple fact. So let me assume that the basic part, this part on the base is absent. My 3 form is just the chain assignments. This is a simplest situation. So my 3 form is just chain assignments of some connection. And then it's easy to verify that. So there are several facts. One fact is that, remember, we have a notion of stability and a sign of a 3 form. Right? Stability is, well, I define it here. Stability is lambda omega non-equal to 0, and negativity is negative sign of lambda. And I already defined for you a notion of definiteness and a sign of the connection. So first claim is that these two notions agree. So when the 3 form is stable of positive or negative type, the connection, the connection that appears here, is definite of positive and negative type. These are exactly the same notions. This is one way to understand where the 3D notions come from. They come from the 6D construction. Then another important fact is that when 3 form is a chain assignments of a connection, then these two different ways of defining the connection agree. The connection, the geometric way of defining the connection, thinking about almost complex structure and what it does, that notion of connection agrees. It's just the same notion of connection that appears here in chain assignments. This is, again, a simple calculation. And then another fact is that, remember, our almost complex structure defined by omega defined a metric as well. So the metric defined is the one that we already encountered in the 3D story. That metric will agree with the metric defined by the connection. This is, again, a calculation. This is not hard, but I would need a board to show it. So the point here is that all 3D notions that we introduced earlier arise as 6D notions. You embed, you start with a connection of a 3 manifold, you think about it as a Lie algebra valued 1 form in the total space of the bundle, you construct this chain assignments 3 form in the total space of the bundle, and then you just apply the natural notions in 6D, and then these are the 3D notions that we already encountered. Another fact is that Hitchin functional evaluated on the chain assignments 3 form is a constant multiple of the pure connection action for 3D gravity. This is again a simple calculation. Because this is not surprising, because what Hitchin functional computes is a volume, and what 3D gravity pure connection functional computes is a volume. So volume is given. And of course, the multiple here is the volume of SU2, the volume of the fiber. So I can summarize all this by saying that pure connection 3D gravity is just the 6D Hitchin theory for Chern-Simons 3 form in the total space of the bundle. This is the way you lift things to 6D. You just consider Chern-Simons 3 form in the total space of the bundle and use the Hitchin natural 6D constructions. And just again to repeat, because this is the essential geometric point, metric arises from the connection, because from the connection you construct 3 form, from 3 form you construct almost complex structure, and almost complex structure gives you a notion of connection and the metric. This is the explanation why connection defines a metric. This is the geometry. It's a very simple way of phrasing all this. Okay, so summary of 6D construction, and then I'll give a summary of the whole talk. So in 3D, or rather, all 3D geometric information can be encoded into that Chern-Simons 3 form in 6D, in the total space of the principal SU2 bundle. I've described to you the case when the 3 form is just the Chern-Simons 3 form for a certain connection. In general, it's Chern-Simons of some connection plus closed 3 form on the base. So in general, when you add this closed 3 form on the base part, you get a bit more complicated story, and you get 3D gravity equations coupled to topological 2 form field. So there is a certain little modification that you get, but the theory in 3D that you get is still topological.
So for
Yeah.
S3, just the round metric on S3, what's the complexity of that?
It will not work for S3. The connection is positive, so it's not the negative case. But it's very for H3. For H3, it's easy because H3, remember, is SL2C mod SU2, and the total space of the principal SU2 bundle over H3 is just SL2C. So of course, what you get is SL2C in that case. So that's the simplest case. And of course the Hitchin 3 form in that case, the one that gives you the complex structure, is just trace G minus 1 dg cubed, where G is the coordinate. That's how you see. So of course it was known to mathematicians, very well known, that if you look at hyperbolic manifolds and take SU2 bundles over them, or frame bundles over them, these guys are naturally complex manifolds. So this fact was known. This is not new. The new interpretation here is adding this pure connection description and phrasing things.
So for S3, it's like a split complex structure. You've got the two. I mean, you've got a J squared equals 1 instead of minus 1.
You got J squared equals 1. Yeah. You're in a different orbit. You can take this Chern-Simons 3 form, but it will not give you complex structure. It will give you something that squares to 1.
And so the total space is S3 plus S3 with vibrations going.
Exactly. Okay, so this can be summarized by saying that 3D gravity is a dimensional reduction of 6D Hitchin theory, where you dimensionally reduce on S3. And then the summary of my talk. So the first point that I explained was that it's possible to describe 3D gravity in terms of connections rather than metrics. And then the explanation for why it all works is this 6D construction. You think in terms of Chern-Simons 3 form in the total space. And therefore 3D gravity can be thought of as a dimensional reduction. And if you perform honest dimensional reduction, then you see a bit more than 3D gravity. You also see 2 form field on the base. So it's 3D gravity coupled to sort of topological matter. And I'm explaining all this, of course, because similar things can be done in 4D with more interesting results. But that will be explained tomorrow. And I want to finish with some interesting open questions here, something that I would like to discuss with other people. So one is a question about the usefulness of the volume gradient flow for connections. This this is a new flow. Is it doing interesting, useful things or not? And the second question that is quite interesting, but actually I know very little about how to approach it, is a question about quantization. We know how to quantize 3D gravity rather well, but because 3D gravity is a dimensional reduction of this 6D Hitchin theory, there is a natural question, can we use the intuition that we get from 3D for quantization of 6D Hitchin? 6D Hitchin is a topological field theory of a complicated sort. Nobody knows how to quantize it. And 6D Hitchin is believed to be related to topological strings, but nobody knows how to quantize it. This way of thinking about 3D gravity as sitting inside Hitchin, I think it gives a new perspective on quantization. Thank you.
Wait for tomorrow to find out whether the
Right.
4D Einstein gravity is a reduction of G2.
No.
Yeah, sorry.
It's more interesting story.
What about like a BTZ black hole? So H3 is just SL.
Locally, it will be SL to C mod some discrete group.
Yeah, okay. But that's okay. So
That's it.
So when you have that 6-dimensional 2-form that has 20 components,
3, 4.
sorry,
Yeah, it has 20 components, yeah. Mhm.
um,
Some of its components disappear because of a symmetry assumption. And so we can do the count. This is useful. Maybe what you're asking is why is there a connection sitting inside 3, 4? Is this the question?
so I had a comment that there's a 6-dimensional theory with a self-doing 3-form. It's the n = 2 theory, chiral theory. And that is believed to have something to do with gauge theories in lower dimensions. So I was just wondering if you took your formulas and you imposed a further constraint, is that
I think that, well, to define notion of self-duality, you need some metric in your 6D, right? So this is already not this setup. Here I don't have any metric. I just have a 3-form,
so you have
nothing
no way
else.
of doing that?
Yeah. So that's the main difference. This is just a theory of 3 forms. But it's amazing that one can think about gravity with all its metric and other geometry of it as a theory of 3 forms. In some high number of dimensions. I think this is when we discovered this fact, we were quite amazed by it. One can look at all of the geometry into just a single object, 3 form. Of course, this object has lots of components, so it's not surprising that it knows about the metric. But it's just a single object. Right? Forms are easier and simpler than metrics. Forms are more God-given, so to say, than metrics. Forms just exist. Metric is a more complicated gadget. So it's amazing that you can encode the metric into form. Because it's not, I mean, it's known, but here it's described how this works for the case of 3D gravity.
Two of the tokens, what time?
One talk is at 10, will be given by Joel, and another talk is at 3 at the same time.